We're looking at the second part of condensation polymers here, and today we're going to look at polypeptides. So let's have a look and see what we've done already on condensation polymers. So we know that there's three types of condensation polymers. There's polyesters, polyamides and polypeptides, and this is the area that we're going to look at today. We know that polyesters are made of two functional groups. They're made of dicarboxylic acids and diols. We know that polyamides are made of diamines and dicarboxylic acids. Now we're going to look at polypeptides as well this time. Now, the first thing I'm going to say is that polypeptides are also polyamides, okay? And we'll call them something else. And there's a reason for that, which will become clear in a little second. So polypeptides are polyamides. That's the first thing that we're going to write down. Okay, so polypeptides are also polyamides, but they're made from different things. So we know that a polyamide is made from diamines and dicarboxylic acids. That's not how you make a polypeptide. Okay? Polypeptides are actually made from a single amino acid monomer, or many different amino acid monomers. In other words, you haven't got two different monomers. There could be just the same amino acid monomers. We're going to look at what an amino acid is in a second as well. Or you could have different amino acids, but you haven't got, let's say, a dicarboxylic acid and a diamine. They're all amino acids. Okay. Right, let's just remind ourselves on what a diamine is and a dicarboxylic acid. So remember, a diamine is that, and a dicarboxylic acid is that there, okay, and they obviously form a polymer, and that polymer that they make is a polyamide, okay. Now, what we're going to do here is we're going to draw a molecule where on one of the monomers we have an amine group and a carboxylic acid group, and we'll call that a amino acid. Okay, so let's have a look. So we've got an amine group here on one monomer, and the other side of the same monomer we've got a carboxylic acid group. That is an amino acid. Amino, there's your amino group, your amine group, and there's your acid group or your carboxylic acid group. So we'll call it an amino acid. Alright? And then we could react that amino acid with a different amino acid. Alright, and that's what we're going to have a look at now. So on this page here, we're going to make a polymer, we're going to make a polypeptide out of amino acids. So it could be something like this. I've just put an extra CH2 in there, just so you can see it better when we draw the peptide which is going to be made. So same thing happens as making a polyamide, in that the CO bond breaks and the NH bond breaks here to eliminate a molecule of water. Now what we're going to do is we're just going to, instead of adding millions of these monomers together, we're just going to add 2 together first of all. So I'm not going to add another one on this side. I'm not going to add another one over here. I'm just going to add these 2 monomers together, and we're going to draw what we're going to make. So I have an NH2 on the end. So this is not a polymer. This is just 2 monomers added together. We've still eliminated a molecule of water though, because we've joined 2 together. So there is still one link point. Right, plus H2O there, like that. So let's have a look at the bond that we've made. We've made a CN bond here, this CN bond here. We call this area here, these 4 atoms here, the amide linkage. Sometimes it's called the peptide linkage. It's only called a peptide linkage if your monomers are amino acids. If your monomers are dicarboxylic acids and diamines, we just call it an amide linkage. But a peptide linkage is an amide linkage, and that's because a polypeptide is a polyamide. Remember, polypeptides are made from amino acids, and polyamides that are not polypeptides are made of dicarboxylic acids and diamines. So let's have a look at what we've got here. So we've got a peptide linkage, so we've made a peptide. It's not a polypeptide because the word poly means many, isn't it? Like millions of them. There's only 2 monomers in this peptide, so we'll call it a dipeptide. So this here is what we'll call a dipeptide. Those of you who do biology might recognise this sort of structure. Okay, so that's what a dipeptide actually is. Okay. Now, the greatest thing about these is that what we've got is we've got lots of different amino acids. Okay, so there's about 20 different varieties or types of amino acids that are naturally occurring. If you think about how many combinations that would be, you could probably sit and work it out actually, how many different naturally occurring dipeptides there would be. Obviously there'd be more than 20, alright? So you've got different types of dipeptides that can be made, and what we can do is we can actually take these dipeptides and link those together to make what we call a protein, okay? So a protein is essentially a long string of amino acids. So lots of amino acids linked together, as in more than 2, would make what we call a protein, right? A protein is just a natural polymer. It's a polypeptide. You could say it's a polyamide as well. That's what a protein actually is, okay? And that's how you would make a protein. In the next topic, in topic 30, you'll look at a little bit more detail on amino acids and proteins. But it's worth just touching on this now, just to know what a polypeptide actually is, to make the link that actually this is just a polymer. What you've got to do is, as well, you've got to identify the repeating unit of a condensation polymer. So you might be given the polymer like this, yeah, or even a really longer one like that. And then you have to identify what the repeating unit is, all right? And the best way to work out the monomer and the condensation polymer is to try and recognise the links formed by the familiar functional groups. Okay, so let's just recap that. So if we have a little table here, so we've got monomer 1, monomer 2, and the polymer that it makes. Sketch a rough table out here. So monomer 1, let's say monomer 1 is a dicarboxylic acid. Do you remember what a dicarboxylic acid looks like from part 1 of this topic? And if we take a dicarboxylic acid, we can react that with a diol. And we know if we react dicarboxylic acid with a diol, you get a polyester. And this would be the repeating unit of the polymer. So what I'm doing here is just summarising this in a table, really. With our polyester there. We can also react a dicarboxylic acid with a diamine to make a polyamide. So there's a polyamide. Or we can find a molecule with a carboxylic acid group on it and an amine group on the same molecule. In other words, an amino acid. And you might have a different amino acid there, or you could have the same one. Now, if you look at this structure here, this is a structure if the amino acid is the same. Okay. Now, if the amino acid is different, then the repeating unit would be 2 monomers wide. But this particular repeating unit, because there's only one type of amino acid in it, there's only 1 monomer wide. In your exam, then you would be expected to identify the repeating unit if there was 2 different amino acids in there. Okay. This one is relatively small though, because there's only 1 type of amino acid. We call these ones polypeptides, which is just a type of polyamide. Okay, now what we're going to look at now is we're going to look at how an amino acid is broken down. All right, so how a polymer is actually broken down. I've just done a carbon chain there using skeletal formula. This is the sort of thing you get, and then you've got to identify what the monomers are. So you could be given the polymer, and then identify what the monomers are. So the first thing you've got to do is, you've got to identify what the repeating unit actually is. So let's see if I can identify that first. So we've got a C double bond O attached to a hydrocarbon chain. Let's see when we next see a C double bond O attached to a carbon chain. Okay, so great. So these can't be in the same repeating unit. And let's have a look here. So we've got a C double bond O bonded to an A. So our repeating unit, if we look, is from this C double bond O here, including this one, to the next one over there. Okay, and what you've got to then be able to do is you've got to take a polymer like this and then work out what the monomers are that make that polymer. Now, when we are making a polyester, in this case, we know it's a polyester because it's got these ester linkages. If you have a look at the bonds which are formed to make a polyester, so we flip back in our notes. When we're making a polyester, what we're doing is we're linking the O from the alcohol with the C from the carboxylic acid. So the O from the alcohol with the C from the carboxylic acid. So what we need to find is, we need to find an alcohol and a carboxylic acid in here, and work out which bond was actually formed when you make the polymer. And it's this bond here. So that bond there was the one which was formed. So we're forming a bond here from the O from the alcohol. This is the new bond that was formed. This must be the O from the alcohol. And this must be the C from the carboxylic acid. Let's put Ca. Ca stands for carboxylic acid. Please don't use that abbreviation in your exam. I'm just running out of space there. So if this was the bond that was formed, then therefore we can work out the structure of the original carboxylic acid, or dicarboxylic acid in this particular case. So it must be this bit here. So we could break a polymer down back into its original monomers. So hydrocarbon chain here, C double bond O, A, C double bond O, we've broken that bond, so therefore that of this C here must have been an OH, and that OH ended up being part of water when it was made in this direction. And this is an O from an alcohol, so I can now draw the structure of an alcohol. So I have an OH, B, OH, and when this bond here is formed, that's the new bond that's formed there. So that would form, that would be the other part of the next monomer along. So these are the two monomers that make up that particular polymer. Okay, so what we're doing here is we're removing a molecule of water. So adding a molecule of water in this direction, removing it in this side. So if we put plus H2O there, like that, and we'll call that hydrolysis. And hydrolysis, we say that this polymer here has been hydrolyzed. So it's been hydrolyzed into a dicarboxylic acid and a diol. Okay, now the reason why we're looking at this hydrolysis reaction, turn the polymer back into its original monomers, is this is how we dispose of condensation polymers. So condensation polymers can be broken down by hydrolysis. which means they're biodegradable, okay? So they can be broken down by hydrolysis, which makes them biodegradable. So it's basically, hydrolysis is the reverse reaction of polymerization. That's what that is. So if you see a condensation polymer, the advantage of condensation polymers is that they are biodegradable. However, if you've got something like an addition polymer, now you would have studied addition polymers in year 12, and you also would have studied them at GCSE. So for example, let's remind ourselves of what addition polymers are. So something like polyethylene or polypropylene. So polyethylene and polypropylene are not biodegradable. And the reason why they're not biodegradable is because basically what polyethylene and polypropylene are, they're essentially massive long-chain alkane molecules. And the properties they have very, very strong carbon-carbon bonds. So with strong carbon-carbon bonds, which are really difficult to break back up into the individual monomers, and non-polar carbon-carbon bonds and carbon-hydrogen bonds. So they're not going to react with anything in the environment. They can't be biodegraded. So we've got unreactive, non-polar, carbon-carbon and carbon-hydrogen bonds. So they're not biodegradable. And these carbon-carbon bonds are dead strong. So you can't break them up. But condensation polymers you can. So that's an advantage of condensation polymers. Alright. So, however though, if we wanted to do something with our polymers made of addition polymers, what we can actually do is we can burn those. So we can burn addition polymers and we can get heat from it and use that heat. However, one of the problems with doing that is that when we burn anything, we get carbon dioxide produced, which is a greenhouse gas. Also, if you take polystyrene, which again is an addition polymer, what can happen is you can get poisonous gases of styrene produced. Okay. However, we don't get that with condensation polymers because we don't need to burn them to dispose of these, because actually what we can do is we can react them with a strong solution of acid and a strong solution of alkali, and you can break them down individual monomers, so we can essentially get back our original monomers. Okay. These ones though, you would either need to burn them to get some heat, or would have to recycle them. So we have to burn or recycle. Obviously burn has some problems. The fact that we have CO2, which is a greenhouse gas, and we have poisonous gases produced as well. Here's my toxic symbol. It's supposed to be skull and crossbones, this. Toxic gas, there we go. So the other method is to recycle. If you can't break them down, in other words, you do them and put them in other uses. So what we can do is we can recycle it, and then that stops it going to landfill. However, there's an issue with recycling in that you need to collect the plastic, you need to transport it, you need to sort it, when all of that uses energy and manpower. Okay, so if I have just a way of either burning it and get some energy from it, and maybe not releasing some poisonous gases, that would be great. Or we could use condensation polymers and just break them down using hydrolysis and get the original monomers back again and make something else. Okay, so that's basically condensation polymers finished. It's a relatively short topic, but quite a lot in it.